Okay, thanks everyone. It's an honor to be the first to present our work. As mentioned before, we are part like a consumer of the network. So today I'm going to introduce about HPNL, which is a lightweight user-space library in Spark. Well, we designed to currently it's using Spark, but it's actually based on our previous CEPH work. We want to build a protocol, agnostic library that can be used by a lot of big data applications. So this is a legal notice, which talks about the trademark stuff. You probably noticed that some with Arista is the other companies' trademarks. This is the performance disclaimer. So the performance might be changed if you are using different optimizations and different hardware. So here comes today's agenda. First, I'd like to share some background and motivation why we are doing this. What's the problem we saw in today's big data application, and how RDMA and the high performance fabric can help to improve the performance and resolve the bottlenecks. The second thing I'm going to talk about the current approaches in the big data software ecosystem. What other guys are doing for the RDMA enabling in the big data applications. The third, I will talk about the design and kind of a micro-benchmark performance of HPNL. What motivated us, how we kind of converted the previous work for the CEPH into this standalone library, user-space library. The fourth one is more like a case study. We showcase how we combine HPNL and the latest persistent memory to use it to improve Spark SAFO performance and address the SAFO bottlenecks. So we present some kind of the terasort performance result and compared with the traditional TCP/IP implementation. And we also will present how this can extend to the future of the remote SAFO, or what we call a remote in-memory accelerator scenario. Last one, we will take a summary and look at the next steps. So we work a lot on big data analytics technologies. We cover like Spark, Hadoop, HDFS, Alexio, a whole bunch of big data analytics softwares. So the problem we saw today is a lot of CSP customers, they start to deploy RDMA NICs in their cluster. So, but the problem is they won't see the big performance improvement simply, install the hardware and running on top of it. So today the network messenger in Spark is based on NATI, and for example, it's not that kind of a high performance. If you simply switch your NIC from 10 GB to 40 or even to 100, you won't see too much performance improvement. Spark is actually the most popular real-time processing solution people are using today. So in its core feature or core component, it had a feature called suffering, where it's really I/O intensive and network intensive. So that's the component where we're trying to using this HPNL to address the shuffle bottlenecks. Previously, there are some works like SPARK-RDMA and the OSU work, they already proved that by using RDMA, we can address this problem. So this leads to our motivation. We want to deploy a lightweighted network library based on Libfabric. The core reason why we choose Libfabric is because it's kind of a protocol agnostic. You can support different types of protocols, each vendor independent. And the second thing is, if we build a library, a user-space lightweight library on top of it, and it can be used by the program. So as a software programmer or software developer's point of view, RDMA is still complex to them. So what they want is something like the traditional socket programming model. They can simplify the programming effort. So that's one of the biggest modifications. So the third and the last thing is actually more important. So today's most big data application is actually based on Java. So they want a Java API on top of it. They do not, I assume that they do not want to rewrite the Genie application to call the C libraries. So that's why we also provided C and Java API in the HPNL library. This is some kind of a background. The left picture is released by the Ethernet Alliance regarding on Ethernet roadmap. So the bandwidth of the NIC has been increased dramatically in the past like 20 years. It increased from 10 megabytes per second to 100 gigabytes per second. And the message RTT time latency has been reduced by orders of magnitude. But I quoted the Creo performance result on the right picture, so we can see that. If you simply switch the hardware without optimization on the software part, or without rewriting the applications of your network messenger, we cannot get the benefit of the NICs. For the typical workload like TerraShort, PageRank, and the SQL workload, the performance gain is really little if you compare the 10 gigabyte network compared with the 40 gigabyte network. So let's see how people are usually doing the RDMA enabling in current big data ecosystem. So there are multiple protocols in current big data applications, and there are multiple libraries now. The most popular one is NetT. So NetT, I will introduce NetT more in the following page. So there are, so for our knowledge, we have been studying like SPARK-RDMA and HiDB project from OSU. Those pioneer projects kind of demonstrate that RDMA can significantly improve Spark performance and also the Hadoop workload, Hadoop performance. So there are some performance numbers they provided. It's like 2.6 times performance compared for TerraShort workload, and also PageRank, the execution time also greatly reduced. For this approach, you need to enable RDMA in each application. It's kind of a by application scenario. For example, you need to enable it in different kind of libraries. So the benefit is it's much easier to get integrated with your big data application because there is little dependency. You can file a Jira in the open source community and submit your code there. But the cons is it's kind of hard to benefit the all big data applications. You need to integrate back case. I can do one for Spark, I can do one for Hadoop, I can do one for Alexio. So, but even with this case-by-case enabling, when you talking from Spark to HDFS, you can still not get the benefit of the RDMA. So you cannot enable cross-stack optimization. So here comes the second approach. So why we do not, convert existing the most popular network messenger widely used in big data applications like NetT, we converted it to Libfabric based, and through this way we can enable in RDMA. So the thing is, this is pretty hard because it's really hard to implement all the interface in NetT transportation layer. And it's also the same thing is you cannot get the cross stack optimization, which means if you only enable RDMA in NetT, when you're talking from Spark to HDFS, still cannot leverage the RDMA. So the left picture is actually we self-developed a ping-pong benchmark compared with NetT and RDMA. We can see that NetT's performance is still not very good. NetT is an asynchronous event-driven network application framework. So it maintains high-performance protocol server and a client. It greatly simplifies the end user, the developer development model. So it provides a uniform API. So you can, whenever you are using NetT, you can use the same API, and it also provides a highly customized program model. So that's we think the two biggest reasons why it's most popular in big data applications. So the third approach is there are some projects are starting to focus on the full stack optimization of a data store. The pioneer projects here comes like the IBM Creo project, which is a high-performance distributed data store. It's designed for sharing of the ephemeral data. So ephemeral data means like a cache, like Safo, but it's kind of end-to-end RDMA enabling. So when you are using this project, you kind of have to load their library at your client. So it leverages a user-level I/O to access hardware directly, bypass the kernel, and also it can deliver like a bare metal I/O performance with very low latency. So the FlashNet is another project. So when they design the project, it's kind of they take both network and storage into consideration. They're using RDMA to remove the user interaction and also doing some file system optimization. Octopus is RDMA-based persistent memory distributed storage. So the key idea here is instead of using DRAM as RDMA memory region, they are using persistent memory directly. So in this way, you can avoid a copy from the DCPMM, from the persistent memory to your DRAM, avoid memory copies. So this co-design over network and storage, we believe this is the future direction, but currently it requires a lot of development work. So for HPNL, we actually choose the first approach, which is to build a standalone library that can be shared by a lot of applications, but it's done not that kind of complex as Netty. So we're trying to keep it as simple as possible. Okay, so here comes the HPNL design. The first is, I assume I can skip this page. So the reason we choose Libfabric is it's friendly to application developer. It's transportation protocol agnostic and easy to port and migration to new hardware. So if we take a look on where is the position of HPNL, it's kind of a general purpose network library. It's user space based, and it's kind of in the same position as Netty, CEPH, and gRPC. But the difference is it's going to support multiple protocols because we are based on Libfabric. And by integrating this library into the existing network framework or network messenger, we can easily be integrated into different big data applications. This is our previous work. Last year we presented the RDMA work in CEPH. So at that time we were based on the async messenger. We say the CEPH messenger framework, and it supports multiple protocols like TCP/IP, RDMA, InfiniBand, and even DPDK network. So at that time, when we developed that, when we're trying to enabling our work in CEPH RDMA, what the pinpoint is we need to spend quite a lot of time on RDMA connection manager stuff, and also the QPair centralized memory pool for receive queue. So after that work, we were wondering why don't we extend the library, the work to build a developer-friendly library for big data applications. So based on the previous work, we changed the design and come up with HPNL. So this is like the architecture. But at the bottom, we have the server, and which can run up to 3 SQL services. And we can run single EQ service. The SQL service will handle the buffer management, the user-defined callback, and also directly call Libfabric APIs. On top of the SQL service and the EQ service, we have the demultiplexer. So for the HPNL interface, currently we have Java and C, C++ interface. This design leverages the RDMA zero copy approach. So because we are using this, it can provide high performance for the network applications. And for the threading model, we were actually using the proactive model. For the demultiplexer layer, we're using both interrupt and polling approach to optimize the HPNL threading model. And for the CQ service, we could bundle it to a specific call to improve the performance. So currently, the overall status is we were on the internal open source process. So it is expected to be open sourced in Q2, by the end of Q2. Below are the micro-benchmark performance. So we conduct a micro-benchmark performance to try to see how this library works. It's based on the Xeon E5 platform, and together with Mellanox 40 gigabyte NICs. We are using Arista 7060 switches. So the test scenario is really simple. We write a simple client-server application and kind of transferring 4K sized message like 1 million times to evaluate the latency. So this is a quick performance comparison. We do two types of a test. The first is the message size testing. We try to evaluate the performance with different message size. Its scalability is pretty good. The second test is the connection scaling test. So we try the different message size and also try different. The first method is 64K and the second is 4K. So we compare the throughput and the scaling. So the throughput is pretty good because we can kind of hit the NIC's throughput, NIC's hardware limitations. And for the latency, we can see that once the concurrency increased once you have a better concurrency, the latency is also pretty good. The lowest message round trip time is like 3.8 microsecond. So you may be wondering why at the first, when you have a low concurrency, the latency is not that good. It's because we do not have, first one is because we do not have the higher concurrency. The second thing is we were still based on, we were using RDMA messenger instead of IMA to doing this ping pong test. So we are assuming that if we are switched to RDMA, IMA, the latency will be better. The third thing is we're using Rocky V2 on Mellanox Connect 4 NICs, and if we are using infinite band switches, maybe the performance the latency will be lower. So here comes the fourth part. How does HPNL performance looks like in a real workload, in a most typical workload? So this part we tested together with the persistent memory. We combine HPNL together with persistent memory and to use the persistent memory as SPARK device and leverage the RDMA network to see how the performance looks like. So this is the SPARK process. It's kind of a bit complex. So in SPARK, when you're trying to load the data from the HDFS directly, it will split the HDF files into splits. So once the split is loaded by the map job, it will do first using the user-defined mapping function to convert it to a pair of key value pairs and into a memory buffer. The memory buffer have some kind of a threshold. If you reach a certain limit, like 100 megabyte, it will be spilled to the local drive here. So the local drive, before it do spill, it will first call the partitioner to do a hash function of the keys to decide which part of that data goes to which reducer. So here we can see like the different colors. Here represents the different kind of keys after you hash them going to the same reducer. And after the partition, we will also get a sort and merge the data, and the reducer will pull the data from the map output file and doing the final short job. So you can see that Safo plays quite a lot. It's really intensive. And for the terabyte workload, for example, if you are doing a terabyte 10 terabyte sorted, half size of that data, 5 terabytes need to be suffered. So it's in the real world deployment, people will try to avoid SAFO as much as possible, but it's not avoidable, even if you using the large memory size. So what we see is the customer is striving to trying to optimize the SAFO performance. So here comes the persistent memory of Fabric P memory with HPNL co-design. The left picture is the current SAFO process, where you serialize the Java object into byte buffer to off heap, and then write that object into the SAFO file, which is a local directory, and then transfer that data through TCP/IP for the remote read, for SAFO read. And then in this PMOF co-design, we have we leverage the persistent memory as a SAFO device, so the object can be stored on the P memory directly. And then we use the PMDK library, which can bypass the kernel and the file system overhead. And then we using HPNL to send that data directly to other nodes. So if we're comparing the two approaches, we can see that with RDMA and persistent memory, we have no context switch, we have efficient read-write on the DCP memory, and also the RDMA read we're using RDMA read for remote SAFO read. So for the performance evaluation, the first thing is that we want to see how RDMA works in the SPARK SAFO. So this one is a simple POC cluster trying to evaluate the RDMA and the TCP/IP performance difference. So it's a 3-node cluster, very simple. We were using HDD as a SAFO device. So to simulate IO-intensive scenario, because we don't have such kind of a huge setup, so we were using NVMe SSD as the HDFS data storage, but using HDD as a SAFO device. So in this case, we clearly create a scenario HDD will be the bottleneck. So for the performance comparison, we can see that HPNL-based RDMA is 1.5 times faster compared with TCP/IP for terabyte 500 gigabyte shot. So the difference, execution time of the terabyte, because the system is kind of configured with the huge DRAM. So there are page cache impact for terabyte because it's using the buffer write for the SAFO files. Then we're doing a performance evaluation of a PMOF. This configuration is a bit complicated compared with the previous one. We have multiple devices as SAFO drives. We're using HDD as a SAFO device. We're using DC persistent memory as a SAFO device. The rest part does not change. So here is the performance. It also using SPARK terabyte workload is 1 terabyte. The left bar is the hard drive short time, and the red bar is the DC persistent memory and HPNL short time. So we can see that the P memory plus RDMA is like 9 times faster compared with HDD. We also using NVMe SSD as a SAFO device, but it's not kind of that fast compared with NVMe SSD. So we were thinking about the last picture is about the latency. So we calculate the read block time, the detailed latency of the SPARK SAFO process, and trying to compare the latency between RDMA and TCP/IP. So it turns out that this P memory and RDMA co-design is most friendly for latency sensitive workload. So its tail latency is improvement is very significant. It's like 1,300 times reduction on the tail latency. So if we go into the SPARK UI and looking on the matrix details, we can see that the SAFO read block time here for HDD is pretty huge. The max SAFO read time is like 15 minutes. But if we're using P memory and RDMA, it's only like 8 seconds. So it's a huge reduction. So that's the performance of P-memory and RDMA co-design. So we'll also start to think about what's the next step. So we were observing that a lot of large big data cluster, we are trying to do compute and storage disaggregation. So which means their traditional Hadoop and Spark, they are tightly coupled. It means the compute engine and the storage, they were on the same node. But you know, compute and storage, they do not grow at the same rate. So the large CSPs, they are trying to separate it. And when they separate it, they also wanted to do a standalone layer for the SAFO. So this is what we believe will look like in the future for the big data clusters. We will have a shared storage as a SAFO layer or as the accelerator layer. So elastic deployment of compute and storage disaggregation requires an independent SAFO. So here we think where the HPNL can help a lot. We can integrate it into their computer layer to improve the computer communication performance. We can also integrate into their shared storage layer like HDFS. Today, most of the approaches, they are based on the HDFS solution to implement the shared storage layer. So there are a lot of ongoing efforts in the Spark community working on this project. So that's why in the future, you know, we can using persistent memory as a shared storage layer and combine it with RDMA to make this new scenario adopted the RDMA technology. Okay, here comes the summary. So based on our observation, the TCP/IP cannot benefit with the new hardware. So we need RDMA optimized user-friendly application, user space library that can be easily integrated into big data applications. So that's why we developed HPNL. It's based on Libfabric, protocol agnostic, and it's faster than TCP/IP. We also showcased its benefit with the persistent memory of Fabric. So for the next, we will open source and deploy this HPNL with persistent memory Fabric in the external SAFO cluster. Okay, thank you. Any question? Okay, thank you.